Welcome to today's class. The topic is on the MAC layer. Tomorrow we'll have a clicker test, and the topic of today is not on the program of tomorrow's test, as we have already discussed. The MAC layer is perhaps for us the simplest because it's done in hardware, so we don't do much with it, but perhaps it is a bit tricky to understand why, and you hear things like layer 2 versus layer 3 networking, and there's a lot of blah blah and incorrect statements about that. So we'll try to go through things in order and bring clarity among the different misconceptions that you can see. This figure is illustrating something, the cable nightmare. So the MAC layer is exactly about this. The MAC layer is about solving the cable nightmare. If you have 100 devices in this room and you try to connect all of them with cables, then you end up somewhere with patch panels and things that are full of cable. That's really the problem that the MAC layer is solving. Now the MAC layer exists in two versions, one which is truly shared medium, and another one which uses things like concentrators, hubs, switches that you've started to use already in the labs, and that we'll discuss more. They're all related, but they are physically different, and to understand how all those pieces fit together, we will need to go through a bit of the evolution of the MAC layer, which I normally don't do in this lecture. I give you the result of evolution, but for understanding the MAC layer, we really need to go through the evolution itself to understand. And as I already mentioned, perhaps sometimes in the past, the evolution of the MAC layer is not finished, so it will evolve and it will become very different in the future. It might die even, as we will perhaps discuss later. So essentially we'll discuss the MAC layer on cable system and on wireless systems, which is the state of affairs today. But in reality, this difference is non-essential. The MAC layer was invented in order to solve the following problems. You had in a campus, that was in the 70s. So in the 70s, you had very few computers. A big campus had perhaps 3, 4 computers and perhaps a number of dumb terminals. And the original way of connecting all those equipment together was with telephone networks. So you would use the telephone networks that would provide the cabling and the connectivity, and then you would put a modem, which means from a networking viewpoint, we had point-to-point links between all the devices. Now, people thought that's a bit clumsy, let's do networks dedicated to computers, and believe it or not, the way they wanted to do it is illustrated by this. Let's pull a big cable, coax cable, the same kind of cable used for transmitting all kinds of signals, TV and other signals, and let's connect all the computers to the same cable. So keyword, the cable is the network. That was one of the ideas. And this is how Ethernet came to birth, right? So it's important to understand that this was the job of the MAC layer, is to make that thing work. As opposed to another way of organizing a network where you have a device in the middle, a router, for example, and then you pull cables from all the computers to the router, and then you have to organize the router, which we know how it's organized. It uses the IP layer. That would be a different way of doing it. This was the original job to be solved. Of course, the cable is a bit anecdotal. Nobody would wire today, except for cable TV operators. You recognize perhaps the way a cable TV network is wired. But apart from those networks that are legacy networks and will more or less disappear in their current form in the future, now the way you organize a cable today is with switches and point-to-point systems. We'll discuss why a bit later. But this is certainly the way it is done in wireless systems. Replace, as a thought experiment, the cable here with a radio channel, and you have the same problem. What was the problem to solve? Well, the problem is essentially that of collisions. If several systems speak together, if several computers send data together, IP packets, for example, because we use a shared cable, there might be, or there will be in most cases, a collision. So how do we solve that? Well, the whole goal of information, one of the main goals of information theory today is to understand how to solve that optimally. One of the ways is to do joint coding. So you would code the analog signal in different ways for each of the devices. And then when you receive them, you have to know which code, or try to guess which code was used in order to be able to decode. This is the information theoretic way. It's used in wireless cellular network, in 3G networks. But it's not used in the traditional MAC layer that we see here. And it was a bit science fiction in the 70s. Instead, what was done is what is called in distributed systems a mutual exclusion protocol. Mutual exclusion means you want to find a way to prevent more than one system to do one thing at a time. Here the thing is to speak. So we want to do mutual exclusion of access for transmission, which is easy to do if you have a central point, but the trick was how to do it in a distributed way. So that was the glorious times of TCP/IP research. So you could invent fantastic things by just putting enough complexity in the problem definition. Here we want that those 4 devices have nothing in common other than the cable. So in a completely distributed way, how can you make sure that they can speak without any collision? That is really the problem that is solved by the shared medium MAC layer. So important to understand what the problem is. How is this problem solved? Well, as usual, it's more difficult to understand the solution than the problem. There are zillions of solutions to that problem. They have names like token ring, Ethernet. You see variants of that. For example, if you use power line at home to transmit data over the electric cabling system, you will use a version that has this called home plug. And of course, we all use something similar when we use Wi-Fi. The keywords that we'll see here is essentially CSMACD, which is the principles that underlie the basic Ethernet. CSMACD derives from CSMACA, that derives from ALOA. So let's start from ALOA. ALOA is one of the very first packet radio networks that was done in the 70s in the US, in the state of Hawaii. At that time, the problem was you have several computers that are in fact on several islands, true islands in the ocean. And at the center you have one mainframe, one computer, and on the remote islands you have other computers, and everything is centralized. Remember, in the 70s, networking was store and forward. So the only thing you would do was to send data from one computer to another central point. And that was done over radio channels because you wanted to cross the sea. And how to do it? Well, there are several ways to do it. One is called token passing. You could have the central controller send a message saying in turn, you on the top left can speak, then the top left speaks, then the center you on the bottom left can speak, etc. That's called polling. In other words, you have a master of ceremony that gives the token to speak to everyone. That's the traditional way of doing it. And that's the one we found in networks like Token Ring and FTDI that are not very widespread today. For the Ethernet thinking was typical of computer science. It was like, well, let's do things that work most of the time but are simpler. And the idea is simply, well, let's allow collisions to occur, and if a collision occurs, let's do something after it has occurred. Right? So it's not the way to do programming today, right? You do your code well, you don't do it, and then if you have a problem, you fix it later, we hope. But that is how it was done. So the algorithm is described on this block of pseudocode, which is taken from the textbook that I use as a reference. Essentially, it says whenever a remote has to send something to the center, it sends it. And then the protocol requires an acknowledgement to come back. So you always speak from remote to center. That's the only way of communication. It's store and forward. When I send a block of data to the center will respond with an acknowledgement. If there is something bad happening, which could be a packet loss due to transmission error, but could also be a collision. It could be a collision because another remote did the same thing at the same time, and because we're sharing, in this example here, the same radio frequency for each direction of communication. So there is one radio frequency from remote to center and one in the other reverse direction. Then collisions could occur. If a collision occurs, then the center probably will not be able to decode at least one of the two packets. Perhaps even the two packets will be impossible to decode if they are received with equal power. So if that happens, the two packets are lost. If only one of the two is lost, then the one that is lost will not receive an acknowledgement. And by not receiving an acknowledgement, you declare that that the packet is lost, and you retransmit again. That is the ALOA procedure. Of course, if you retransmit immediately, then imagine the two remotes are sending at the same time, they collide. If the timings are about the same for the both remotes, if they retransmit, they will retransmit at the same time, and then they will collide again, and we're in a deadlock. To avoid this deadlock, we introduce some random timeout, which is explained in more details in the slides that I won't explain here. Essentially, you draw a random number for the timer, which is exponentially distributed, and then you try again. So the probability of colliding again is smaller, and if you collide again, you will retransmit with, you will increase the timeout to avoid the probability of repeated collisions. So this is one of the MAC layer protocols, historically the first one. It's not the first one, it's the first one that is based on what is called random access. Random access means we try to send without coordination, as opposed to token passing, as I expressed before. Then if you do a mathematical analysis, and there were zillions of papers on the performance of the ALOA system in the 80s, in queuing theory, you quickly see that it's not very, very efficient. It's not very efficient if the rate you want to achieve is high compared to the capacity of the channel. Because the probability, as soon as two systems want to speak together, one of the two, and probably the two, will lose the channel, so you will need to repeat, so it's highly inefficient. Depending on the modeling assumptions you do, you can show that the performance you can achieve in the very best case is 18% of the nominal capacity of the channel. So if you have a number of devices that are sending data, if the traffic load on the system is more than 18% of the capacity of the channel, the thing will collide, will be chronically congested. So you need to make sure that total traffic is less than 18%, and then it will work with delays and repetition, but will more or less work. So people have decided to improve on the performance of this, and the first improvement is called CSMA. The only complex thing is decoding the acronym. It means carrier sense multiple access. Carrier is the radio frequency or the Ethernet cable, and sense means listen. So you listen to the channel, and essentially, instead of doing like ALOA, where whenever a system wants to send, it sends, here you first listen whether someone else is sending. Right. Which seems like a good idea, but still makes a number of assumptions. It makes in particular the assumption that you're able to listen, which is a very strong assumption done on Ethernet. Sometimes people say it means the medium is transitive. Transitive means if somebody on the left sends data to speak to somebody in the middle, someone else who's on the right will listen, will hear it. Which might not be true if the cable is very long, but will be true if the cable is not so long, and if the power, this emission power, are large enough or are within bounds that are large enough so that anybody can hear it. That's one of the assumptions that go together with CSMA. Assume you have a system that's typically more local. We're moving towards Ethernet. where if someone is transmitting, you can hear it. Like in this room, if someone is speaking and is speaking loud enough to be heard by me, not like you two guys here now, whispering to each other, then I will hear it and I will stop talking if I'm polite. And so that's the idea of CSMACD, right? If you do this, do you think we can avoid collisions? Clickers. I close it in 5 seconds. And the correct answer is the majority vote. Of course, yes, they can occur regardless of the bandwidth delay product. And here is a way to understand why they can occur. This is again a space-time diagram. Time flows vertically and space is horizontal. Assume A sends at time 0 some data, and the data propagates on the cable very fast, but still not instantly. So the parallelogram is showing the electrical state, if you want, of the cable along the cable. So the waves arrive at some time, let's call it t equal to, at B. Now, even if B is listening, if B decides to start talking at any time before 2, in fact, then this can create a collision, because by the time T starts speaking, then when B sees the channel, it is too late. At time t equal 1, for example, A has already started to speak, but B sees nothing. There's nothing to hear yet, because the propagation time, which is very large for us human beings, but is not so large for electronic devices, is not negligible. So B has done the right thing and is sending data. And we see that the signal will collide. The places where the signal collides are where the two parallelograms overlap. So there will not be a collision everywhere, but in all the middle places of the cable here, there will be collision. Collisions mean the two signals are superimposed, and if they have equal power, they probably destroy each other. Because here again, we don't do codes division multiplexing. So that's the problem with CSMA, with Ethernet in general. Collisions can be avoided, but not all. So we need a mechanism to handle collisions. We could do like we do in ALOA with acknowledgements. The choice that is done for Ethernet is not acknowledgement, is called CD, collision detection. So CSMACD means Ethernet. And the main thing is that instead of waiting for an acknowledgement, which could be possible, here, because we assume the medium is transitive, we assume that we're able to hear that there is a collision. So we start transmitting. First we listen. If the channel appears to be idle, then we start transmitting. If we were like B a minute ago in this vulnerability period where something was being sent but has not yet arrived, there will be a collision, but I may detect it by continuing to listen. If I hear the collision at my place, then I know there was a collision and I will abort, it's a failure. So I will have an indirect acknowledgement or negative acknowledgement without sending any explicit message. So this protocol is called CSMACD, Carrier Sense Multiple Access with Collision Detection. Let's see a small simulation of it. like a minute ago, B starts transmitting very, very shortly after A, but late enough, not so late, so that the channel appears to be idle. Then A will sense the collision, because A continues to listen, and at some point, the signal of B will reach A. So A will hear the collision, and then A will abort. It does not immediately abort. A sends what is called jam bits, which are, I think, inessential here. It's really an abortion of the signal, but we make it, we have to make sure the signal is long enough so that B also hears the collision. Because now, if we're talking electronic systems, we're in the analog world, not in the bit world, so you might very well have a collision that's short enough so that you don't detect it. So the jam bits are making sure the collision is long enough to ensure that everybody will detect it. So B will do the same thing. B detects the collision very shortly after sending and sends a signal that's long enough to make sure everybody detects it. That's CSMACD. So both have sensed that their attempt has failed. Then the rest is as before. You draw a random timer and you try again while continuing to listen. So for example, assume here A has drawn timer T1 and B has drawn timer T2. Whoever fires first will try again. So B will try again at this point. Of course, the difference between the timers are large enough so that if B and A have two different values, then there will not be again in this small window of bad opportunity where a collision could occur. So now B will start transmitting. While A is in timeout mechanism, A continues to listen to the channel. So now A will defer, will also sense that the channel is busy. Therefore, A will not send at time T1, but will wait until the channel is idle. So this is how CSMACD works. And all variants of it, including Wi-Fi, home power plug, power line communication, practically all random access protocol use this with zillions of little variants. That may take a long time to explain, but that's the main idea. Now, this has a few consequences that are visible to us on things we do with Wiresharks and things like this. One first consequence is that those assumptions, in particular that the medium is transitive, require a minimum packet size, which is hard to understand unless you look at this diagram. So assume here, so it's better to look on the left where the colors are better. Look at the scenario on the left and on the right. What's the difference? On the left, the packet sent by A is short. Time is flowing vertically. The length of the packet in time is the width of this blue parallelogram. And assume here it is short. Then what could happen is that A does not detect a collision, because at A, the packet sent by B has arrived after the packet sent by A. So for A, things are perfectly fine. But perhaps the intended destination is C, that's in the middle of the cable or of the wireless channel. And for C, there is a collision because the two are overlapping. So if that case happens on the left, the collision detection mechanism failed. A and B both think they successfully sent, but it's not true. They successfully, B managed to send to A, but A didn't manage to send to B nor to C. Right. So that's, in some sense, a bug in the algorithm. Yes?
Yeah. Why don't B sense the collision when it receives the piece of blue? Yeah.
Well, we assume here B senses the blue thing, so it stops, but because it's jamming, it sends a jam signal. So to make the collision long enough. But yeah, B has, sorry, I said wrong, I said wrongly. B has sensed the collision, but A hasn't sensed it. How to fix it? Well, there's a very easy fix. The fix is to say, well, make sure you send long enough so that if there is a collision, you will always hear it. So, because the problem occurs if the transmission time is larger than essentially the round trip time, the propagation time. both ways, plus the time to transmit a minimum size packet. So if you, minimum size header. So if here in that case, the round trip time is larger than the transmission time, and then A could not sense the collision. So that is what CSMACD imposes, which has a lot of implications. First, it imposes a minimum packet size, and second, it imposes a maximum propagation time, because the two have to be consistent. So the minimum packet size has to be such that the transmission of this packet takes at least as long as the worst case two-way propagation time. Right? So if you have an Ethernet cable that would be 1,000 kilometers, the propagation times that will be of the order of a few milliseconds would impose that you transmit at milliseconds. Now, if you transmit at 1 gigabit per second, you would have huge packet sizes. Right? The Ethernet standard says the minimum packet size is 64 bytes, so 512 bits. So you cannot send an Ethernet packet smaller than that. And this packet size is fixed, which means that depending on the wireline speed, the size of the cables have to be correspondingly short. If you use Ethernet at 10 megabit per second, you can have cable of 2 kilometers. If you have Ethernet at 100 megabit per second, it's a maximum of 200 meters. And at gigabit per second, that's 20 meters. At least if you use CSMACD. So this is why we have all those weird things in CSMACD, maximum cable length, minimum packet size. That's due to the protocol itself. Now CSMACD is synonym of Ethernet, or at least one of the many variants of Ethernet. There are many variants of what is called Ethernet. And it's the one that is typically deployed on coax cable, which you very seldom see today in this form, although in the lab, in the Internet Engineering Workshop, we have a number of cabling systems where we can really do the original Ethernet cabling. You take a coax cable, you put a T connector, you connect your PC into it, and the network is the cable, and you use CSMACD. If you do that, your cable has to be at most 2 kilometers of length. Wi-Fi does very similar things. With a few optimizations, it uses a handshake. So for sending a packet, that's exactly what is done. But when it tries to send very long packet, it will first send a short packet first to test the channel in an attempt to improve things. There are many, many optimizations in Wi-Fi that we will not discuss in this lecture. There is a course on mobile networking that discuss this at length, and you find much more information in the textbook that I give as a reference. We spoke about a minimum packet length. Do you think there is a maximum packet length? And if so, which one is it? It's a guess. I ask you to guess what. It's very good to guess. I mean, first, most of the things we are seeing here, most of the things in TCP/IP are very simple. So by most of them you can guess, and if you guess right, then you don't need to remember how things are done because you will re-guess again when you need, right? So you need to remember only the difference between your guess and the true state of things. So imagine you are working in the 70s in a computer lab and you're designing Ethernet at 100 megabit per second. Then you're in the 90s perhaps. What would you do about the maximum packet size? I close in 5 seconds. Okay, so the majority of you would say there is no maximum size. And it's true if we look just at the protocol. If we just do PowerPoint research with space-time diagrams, we don't need a maximum packet size. Now assume you do an Ethernet adapter, right? You will build an FPGA or something to make the Ethernet CSMA protocol on the cable. You probably want to have a maximum packet size, right? Because you will receive those packets. If you have no clue how large it is, you don't know what to do with it. You will need to store it. You will need to stop the operation when you think the packet has arrived. If a packet can be 1 terabyte, you never know. You continue receiving. You don't know whether the thing has hung or whatever. So the need to store and to know when to stop forces you to have a maximum packet size. The maximum packet size is, in fact, it's probably a mode of this distribution. Yes, it's answer 5, 1500 bytes, 12,000 bits, which is short. It was very long in when Ethernet was invented at the end of the 70s. It's very short for today's technology. But that's when people did it in the 70s, they wanted to be able to build devices, so they chose that packet size. Yes?
Aren't there like jumbo packets?
Now you can. So the questions are then jumbo packets. Yes, you can have, of course, over time, people have realized you can make it larger, and you can have an option in your adapter that allows jumbo packets, much larger packet sizes. However, you have no guarantee that the other end will support that size. So the only guarantee that you have if you start using Ethernet is that all systems will be able to support a packet size of 1500 bytes. So in practice today, if you work in the open internet, you have to generate packets that will never be larger than 1500 bytes. If you work in a well-controlled environment, for example, you're at CERN doing particle physics, and you have terabytes per second or terabits per second of data that need to be shuffled across your accelerator, then of course you can use Ethernet with larger packet sizes because you control the environment. You know all your devices will have that. Let me skip this one, which will save us time. Let me ask another question here. Assume I have a Wi-Fi network with a base station. How many frames can be transmitted concurrently? A frame is a packet. The word for packet in the MAC layer is a frame. MAC layer PDU. I have several devices. For example, I have 3 here. Is it possible that more than 1 frame can be sent in parallel or not? I give you several options. Which one do you prefer? I close in 5 seconds. Okay, it's an interesting variant of the bugs. The correct answer is at most 1 in total, which I guess is, I'm not able to see, but I guess is your majority vote. In other words, the mental model of a MAC layer multiple access LAN, whatever it is the shared Ethernet cable, whether it's wireless radio, whether you have all those zillions of options and sub-messages in Wi-Fi. At the end of the day, the important thing to remember is this is a shared medium domain in which there can be at least one sending of a packet at a time, globally, for this entire domain. This is what a shared medium domain is. Voila, that was the first item of this shared medium MAC layer. Now, if we use the MAC layer in GNS3 in the lab or in offices or at home if you use cable, you have something that's a bit different. You use typically Ethernet switches that are sometimes called concentrators, or if you go to MediaMarkt, they may have any name of network box, or your ADSL modem has often this function. So the first interesting news is that in today's Ethernet environment, there is no CSMACD. There's no shared medium, right? But it's still called Ethernet. And that's the paradox. So how can we explain this paradox? This is where we'll go through all the steps of evolutions. Imagine you're in the 80s and you're doing research on computer networks. Computer networks are starting to emerge in businesses, banks, all kinds of companies for accounting and so on. So you start having those cabling problems. And then you read that in a university they did this Ethernet stuff with a big coax cable. I mean, when I was a student in my office, there was one coax cable that was passing through a hole drilled in the wall, and my computer was connected with, to the cable. Now, assume you want to do this in university is okay. In a bank, you don't do that, right? You don't drill wires in the wall to pull a cable. So what you do is a more organized thing. So one of the first things that people did, like companies like IBM, DEC, and so on, when they sell the same idea to companies, they invented a box called the passive hub, or the hub, which is a place where all the cables terminate. So instead of having this big cable that you connect to, you have your computer that connects to a cabinet, typically in a corridor in a basement somewhere. And in the cabinet, you have essentially a cabling system. So all those T connectors, you could put them here, and you just do some packaging around, and out of nothing, you have created essentially a new product called the hub. Right? So it is exactly the same as before. You still have a shared cable that goes everywhere, but now the cable is in a box. And then you have lobes. So most of the cabling is in fact those access to the main cable, which are called lobes in this context here. That was the first step. Now the second step was to, once you had those boxes, of course, because the imagination and the drive of engineers is endless, so immediately somebody invented a better way of doing it, what is called active hub. So instead of doing a pure cabling system, well, you could say, here I'm sending a signal that contains bits, Ethernet bits, and then I'm just forwarding it by simply connecting passively. Instead of that, if I could do a small system that would be an amplifier, that would be one thing, but even better, I could do a repeater. What's the difference between an amplifier and a repeater? An amplifier is an analog device that takes your signal and makes it stronger. But it makes everything stronger, including the noise that comes with the signal. A repeater is smarter. A repeater is what I can call an intermediate system of layer 1. So let's see that here. A repeater decodes the Ethernet signal, at least the basic of the Ethernet signal. It recognizes the bits. And since so for example, when this is sending an Ethernet packet, it's a sequence of bits. This one recognizes the bits and repeats them here. But by repeating them, we regenerate them. So the level of noise is, the noise is completely suppressed. So we can regenerate here a signal that has the same power as it had here, or even stronger here. That's the difference between a repeater and an amplifier. So the first step was to do boxes that were repeaters. It's more beautiful. It allows to have, for example, perhaps here an optical cable that could be for whatever reason, and then you can change the medium. You could be here optical and here coax, like we saw before. So you have more flexibility, you have better performance. That's wonderful. And incidentally, it gives us our first example of an intermediate system of the physical layer. Nonetheless, the only improvement is in the quality of the signal, but otherwise it's still exactly the same as before. In particular, this is one single collision domain. If A sends to B, then C cannot send. There is the CSMACD protocol that will make sure only one of them sends at a time. Right? So it is logically exactly the same as with the previous case here. Then as a minor improvement, as soon as people did that, well, they realized that what they're doing looks very much like telephony technology, right? If you think about how telephone systems are cabled, you have boxes that are called telephone switches, and then you connect your telephone with telephone cables to a switch, right? Those cables are not shared. They are point-to-point cables. And point-to-point cables are much easier. The coax cables are more expensive. You have to be careful if you bend them. So those cables are called UTP, unshielded twisted pair. Unshielded means there is no coax around it, screen around it. And twisted pair means they are twisted. Why do we twist cables? Yes?
To reduce interference?
To reduce interference and to reduce the reception of interference. So when you twist a cable, you make the two consecutive lobes have opposite orientation. So the electromagnetic waves that they emit are opposite. Since they're very close to each other, they almost cancel. That's for the emission side, so they emit less interference. And the same as you know, the laws of electromagnetism are completely symmetrical. Everything that works for sending works for receiving, so it's the same for receiving interference. So this is why you twist things. If you're sending DC current on your bicycle, there's no need to twist it for wiring your light, right? But for sending alternative currents and in general things that might emit radiations, you do. So that's one, I would say, minor change. From the viewpoint of intellectual viewpoint, it's even a zero change. But from a practical viewpoint, it's completely different. And this is where things break. I mean, originally, people had the idea of having a shared cable, which is a big coax thing to which everybody connects, like cable TV networks today. But at the end of the day, what you have is a box with point-to-point things that people connect to. So very much like a non-shared system. And of course, the next step, once you have that, which is now a major step in the sense of TCP/IP layers, since you have devices that are connected by point-to-point cables to a box, the box is the blue thing here, then you can change the box and do something smarter than CSMACD. And the smarter thing is to put a packet switch, which could be a router. But since it was done in the 80s, at this time, if you ask people to do a router, they ask the question, a router for which protocol? And then you would have to do a multi-protocol router that would support the 20 or 30 different routing protocols that existed at that time. So instead they say, well, let's do a lower level thing that forwards packets independent of the network layer protocol. And that is called a switch. So what is a switch? A switch is something that terminates all the incoming cables, puts a queue, an input queue on each of the incoming cables. So from a physical layer viewpoint, things are point-to-point. There's from A to the switch, there is one physical layer that terminates here. And then there is a processor or an FPGA of some kind that will analyze all the queues here and send them to the correct destination. And then if in particular you are careful that the cables here have have one transmission and one reception side, so which is typical for most Ethernet cables. There are 4 wires. You need 2 wires for transmitting, 2 wires for receiving, which means in particular there is no interference between the 2 directions of transmission. So you can send and receive on the same cable. So this device here has a blue side, receiving, a green side, sending. It receives things. It has to queue because several things can arrive on different input ports. And then it has to pick one and send it on the output port. Right. This is exactly what a router does as well. But a router will do it by analyzing IP packet headers. In particular, one of the things I have not discussed is how does this intelligence here know where to send the packet? How does it know that the packet has to be sent to C? Right. With shared medium stuff, you don't have that question. Everything is sent to everyone, and then you see whether it's for you. How do you see whether it's for you?
MAC address.
MAC address, by analyzing the MAC destination address. So this is what this system will do also. It will analyze the MAC destination address, and hopefully it will know that C is on the corresponding port. Voilà. We'll do a break and resume in 15